In this video, we're going to learn how to calculate the volume element in cylindrical coordinates. Suppose that we have a volume integral in Cartesian coordinates, so our variables are x, y, and z, and the differentials used for the integral are thus dx, dy, and dz. Each of those is a tiny length, and together they form a tiny volume, because length times length times length results in a volume, just thinking in terms of dimensions. Now, the problem is, if we transform this into cylindrical coordinates, that integral is now going to use the variables r, phi, and z. The problem is, again, thinking in terms of dimensions, this is a length, and this is a length, but this is an angle. And length times angle does not result in a volume. For this integral to work, however, this needs to be a volume, which means we need an additional factor that we can multiply with those differentials in order to turn this into a volume. And the way we're going to do that is the following. Firstly, we're going to have to find the Jacobian for the transformation. We already did that in the previous video, and I'm going to link that in the description down below so we can treat the Jacobian as given for this one. And secondly, we're going to calculate the determinant of that Jacobian. And thirdly, we're going to multiply that determinant with the differentials of this integral. So let's do exactly that. Again, just as a reminder, this is our transformation from Cartesian to cylindrical coordinates. And the Jacobian of that transformation looks like this. Now, the easiest way to calculate the determinant for this matrix is to use the rule of sarrus, for which we are going to write the first two columns of the matrix right next to it. And now the determinant of this matrix is this diagonal multiplied plus this diagonal multiplied plus this diagonal multiplied minus this one, minus this one, minus this one. So for the first diagonal, we have cosine phi times r cosine phi times 1. That gives us r cosine squared phi. For the second diagonal, we have minus r sine phi times 0, so that's just going to be 0. For the third diagonal, this one right here, we have 0 times sine phi times 0, so that's going to be 0 as well. And now in the other direction, we have to subtract them. The first diagonal in the other direction, we have 0 times r cosine phi times 0, so that's going to be 0 as well. For the second one, we have 0 times cosine phi, which is 0 as well. And for the last one, we have 1 times sine phi times minus r sine phi. We have to subtract that, so we have minus r sine squared of phi. Two negatives result in a positive, so we have r sine squared phi plus r cosine squared phi. And now, since we have a common factor of r in both of those, we can factor out the r, leaving us with sine squared phi plus cosine squared phi in the brackets. And now we can use the trigonometric identity that sine squared of x plus cosine squared of x is 1, which helps us to completely eliminate this term, leaving us with just r. So r is the determinant of this matrix, of the Jacobian matrix for our transformation. And as a very last step, we have to multiply that r with the differentials. So r is the additional factor we were looking for. And that means our volume element in cylindrical coordinates is r dr d phi dz. If you found this video helpful, consider giving it a thumbs up or sharing it with a friend who might also benefit from it. Thank you so much for watching, and see you in the next one.